In this problem, we're asked to determine if a given function is continuous at a particular value, in this case x equal 4, and the function is given to be a piecewise defined function, and notice that it transitions from one rule to another right at 4. Again, visualizing these sorts of things is a good idea. What we're wondering is, if I was looking at the graph and looking over here where x is 4, does the graph come together or not? If the graph makes a sudden jump from one value to another, or if it has a hole in it, then the answer to the continuity question would be no. But if there's a smooth transition through the function value at x value 4, so the left limit and the right limit and the function value all come together. I'm going to draw this over here because I don't know exactly where to put it on this page yet. But if this sort of thing happens, the left limit, the right limit, and the function value come together, then it will be continuous. If the left limit goes to one value and the right limit goes to another value, then it doesn't matter where the function value is, the answer is going to be no. So the left limit might match, say, the function value, but this would not be. So this is a yes if this happens, no if that happens. So this really means we've got a well-defined set of operations to carry out. Calculate f of 4, calculate the limit as x gets close to 4 on the left on this function, and calculate the limit as x gets close to 4 on the right on this function. You can do these in any order you like, but the idea is that all three of these need to be a value, and they need to be the same value. We want to get them to come together like they do in this picture here. Of the three, the simplest is the algebra question, the f of 4, so I'll start there. I use the top rule when x is 4, so this is strictly a calculation. 3 square root of 4 minus 9. Square root of 4 is 2, 3 times 2 is 6, 6 minus 9 is negative 3. So what I've just discovered on my graph up here is that the function value at 4 is down at negative 3. So the limits, the question are, do they link up to this value, or do they end up somewhere else? All right. So the left limit as x approaches 4 is asking, will the function hook up to this? And if I'm on the left side of 4, the function that we're talking about, f, has the rule, let's see, if I'm on the left side of 4, x is less than 4. So I'm following minus 3x plus 12 over x minus 4. This is a limit question now. That's a limit of a function that has a division in it. So I'm always going to gather my clue on these every time and find out what happens as x jumps right on that number. Again, this calculation over here doesn't necessarily give me the answer to the question, but it gives me a push as to how to approach it. The denominator has a 0, so this is a problem spot. 4 is not in the domain of this piece. 4 is in the domain of the function because we have already found the value, but it's not in the domain of this piece. And if I put 4 in the numerator, I get a 0. So this is a 0 over 0 situation. This clue tells me to cancel the zeros, which means I've got to find them, and it helps me actually find them. There must be a factor of x minus 4 in both the numerator and the denominator. The denominator is obvious in this case. Numerator may be less obvious, but there must be one in order to get that 0 out. So you think about what happens, what else is in there? If I factor out an x minus 4, what is there? Well, I need negative 3 multiplying the x. This must be the number negative 3. And multiply that out, and you see it does match. These two now cancel, and the only thing left is this constant, so it doesn't matter where x is going. This is going to be negative 3. So far so good on the continuity question. We've just discovered that the left limit here is also negative 3. So from the left side we connect up to this value. Now let's check and see what happens on the right side. As I come in from the right, I am using x values larger